Good afternoon and welcome to the Technical Library. I'm Mary Ray, and we have a special program this afternoon that I'm glad you're going to be able to see. Our guest storyteller is not only a World War II veteran who served in China, Burma, and India. He also worked here on the base for 42 years and continues to volunteer his time, splitting it between the China Lake Police Department and the Navy Museum. Please join me in welcoming Mr. Dick DeMarco.
This came through the idea of Ray Hinton. But one of the men in the project was Jim Bowen, and apparently he was doing some diving at San Clemente Island with some other people. And one of the things you run into when you do dive down there in Wilson Cove are the morays, moray eels. So he said that would be a good name for our project. Now, moray is not an original name for a submarine. The first USS Moray was built in 1943. World War II. It was one of the Beilou class and was used extensively in World War II. It was retired officially and sunk as a target in 1967. So Moray is not an original name, but it seemed adaptable for what we were trying to do. Something that would, you fool around with it and it could give you a problem. Next. Now this is what Dr. McLean put together. I have a copy of his original notes, and I don't know if you ever saw his handwriting, but I deciphered it, and this is what he wanted to do. When we finally came to the realization that we had to use aluminum, then he wrote these kind of things. He wanted it to withstand 3,000 psi. Now, for every 2.24 feet of water, you have 1 psi, so this is about 7,000 feet. But actually, we gave it a safety factor. We built it so it would take over 4,000 psi. He wanted regular navigation, aircraft instrumentation, depth and speed gauges, and L was very instrumental in getting all this put together in our display there in the control sphere. And he gave us a target of spending $450,000 to $500,000 for the first year to kind of build all this. He also wanted something in the front of the boat, a kind of a hydrodynamic shape, so that we have little resistance when we go through the water. But now you had right behind it the sonar system, so it couldn't impede the operation of the sonar system. So we went around and found that Goodyear Aerospace could provide a material that in seawater, it didn't impede the transmission of a sonar wave or the reception. So that's what we did to solve that problem. Short range sonar, because we had to communicate with the surface ships. They had to keep track of us when we were operating, as long as long-range passives and active sonar. Now the tail section had to be the part that was different than the fiberglass hull. It had to support the motor, and it had to support the control fins. Could we go on to the next one? This was his idea of a underwater fighter craft. We would have something where you'd use hydrogen peroxide and diesel oil. Now when you combine the two, you get quite a reaction. So with this two systems, we would be able to operate, meter it into a unit, a boiler, where then we would drive our propellers. But this was the next version, the tactical version. And we would have ordnance in the front along with our sonar system. But in the meantime, we had to demonstrate a concept. Next one. People go wild about what kind of ordnance you have, and when the Los Angeles Times published an article about when we did our first test at San Clemente Island, they said the Navy has a small submersible that is able to fire rockets, underwater rockets, with nuclear-tipped warheads. If you fired a rocket with a nuclear-tipped warhead at a ship over here, you're killed in the blast. But this is what LA Times said we had here at China Lake. Next one. This was his tactical moray, the end game, if you will. But again, we had to prove the theory. We had to prove the concept. So this is what we had to do in the meantime. Remember I said we had a pre-flooded hull. This was a upper hull, which would open up one half, the lower half, and we would have all the things that would support the equipment in pressure vessels, the electronic sphere, the personnel sphere, the battery pack, because for the first propulsion system, we used a Westinghouse torpedo motor, Astor torpedo motor. It was a 165 horsepower DC motor, so we had to have a silver zinc battery pack to operate it. We would simply have the motor back here. We had counter-rotating props. Counter-rotating props, a 4-blade and a 3-blade. People keep asking, why didn't you have 4-4 or 3-3? Why would we have an odd number of blades?
Resonance?
Cavitation underwater. We wanted to be quiet. If you have a 4-blade and a 3-blade, you don't have cavitation. We want to have a very quiet submarine. And the other thing is, if you have a free-flooded vehicle, when they're hitting you with sonar, they can't tell what they've got. Is it a whale? Is it a kelp bed? What is it? It doesn't have that sharp metallic ring. Next slide. We went and had Zenith Plastic down there in LA build the mold. Now the mold is used for both halves, the upper and lower half of the hull. And you lay up the fiberglass until you get something about a 1/4 inch thick. Then every so often you build in what we call a rib section to stiffen that. Next one. The nose again was a plastic material called Absonic by Goodyear, but it just gave us that nice hydrodynamic shape so we have minimum drag in the water. Next. This gives you a back end view of the upper and lower hull, our fiberglass hulls, in the mold. Too bad we don't have the mold now. Everything was put into one of the buildings here at China Lake, and after a while they destroyed the mold and everything else that was in it. Typical China Lake people. Next one. This is what we were supplied with when we went to Goodrich Corporation. Next. Now, for the hull itself, you have the 2 halves, and we need stiffeners in them. And these are like little half sections or ribs. And the reason you have these odd shapes in here, because you have the nacelle, the control sphere, and the electronic sphere in between them, and lock that in as you set them in the lower half. The back end would be aluminum, and we'll show you more about that. This is a concept, I think you were involved in putting this together, Al, where the whole concept of the control sphere was equivalent to a small Volkswagen. Same kind of a size for the occupants. And we have 2 operators with a aircraft control stick, and this is what Al came up with, the idea of, since he's an aviator, what we need in the way of instrumentation. Next slide. Now, this is what we received from the Modern Pattern Foundry people in Los Angeles. They made these, what they call a permanent mold, cast them 2 halves. The upper half was different than the lower half because we had to have places reinforced for pass-throughs. Hydraulic fittings, electronic fittings, and our hatch. The lower half was a little different. We brought those to China Lake, next, and we machined them here. And someone here said his dad worked in the machine shop, and those people did a wonderful job. We have the big lathes there. We could turn these things and come up with the final product. And the hatch design, we looked at things like the Trieste. We went aboard the Trieste, Commander Link Lippincott, myself. We had 5 submariners originally in the program. So we would look at what they did with the Trieste, Jacques Picard and his boat. We even went down to see Cousteau and his Sir Coupe when they brought it to San Diego. We wanted to see what that boat had in the way of devices, safety devices. And when we would talk to them, Andre Laban was the designer of their Sir Coupe, their little diving saucer. Commander Link Lippincott and I said, well, what do you have in the way of safety devices if you get in trouble? And they looked at me. I said, do you have pingers? If you get down there and you're locked down there somewhere, can you tell people where you're at? Pingers. No. I said, can you pop something into the float and say, we're here, like we have, little thing? No. Do you have UQC, telephone, that you can talk to people? No. And he got angry and he said, we don't intend to lose the boat. You know. Okay. So we decided we could not learn anything from Jacques Cousteau, his Sir Coupe, and his operating boat. Next. This is the tail section. This would be the part that, after it's machined, would be put onto the back of the boat, And we'd have these big mounting rings, front and back, where we could lock the upper half and the lower half of the hemispheres of the hulls, and then we would bolt this into the ring and it would support it. When we found out that there was only one place in Los Angeles that could make a large, thin wall aluminum casting, we had to go to these people, and they're Lebanese. Their history and background is bell makers, in the Middle East. And they were able to make this tail section, which at that time was reported to be the largest thin wall aluminum casting ever made in Los Angeles. Next one. These are the risers and sprues that you feed that to. Eventually, next one, you get to a point where they're grinding it down, and these are the owner and his brother operating that little Lebanese casting place in LA. Next one. And this is what it looks like when we got through with it. And I can prove I have black hair there. What you do here, you're mounting these parts, you're welding them on so that they can support the fins. Each one becomes a support for the control fins. In the back end, you simply slip in the motor. Next. We had to have a battery pack. Everything has to be protected, pressure housing. So the battery pack was again made out of aluminum. And this had 240 batteries, silver zinc batteries, inserted into a pack inside. Next. This is what was put in. Now what you do, and this is the concept I think Al and the rest of them came up with, you have a control in the control sphere where you can say, I want this much power, this much power, this much power. It says low speed, middle speed, and high speed. You're drawing so much power out of the pack. You're not getting it all at one time. You can go up to 15 knots, but you're using most of the power and you're short-lived. So this is what had to be inserted into that pressure vessel. And after 5 hours of operation, we had to pull this back out and go and take every one of them, discharge the battery, recharge them. We found the bad one, we take it out and replace it. That was critical. When you're charging and discharging a battery, if you found the bad one, you removed it. You didn't try to get by and say, well, the other 200 or so will take care of it. No. Our people were trained to do it in a certain fashion. Next. Now to prove out the concept that we had something that would work at great depths, came up with 1/5 scales of the two aluminums that were candidates. At first I had the metal materials group, the mechanical engineering section. Later on I had to take over the program because these guys wouldn't volunteer and do it. Anyway, we made models of the two type of aluminums, A356 and 224. Now we took these things, made 1/5 scale models, and we put them on a rack. Next one. The people down along the coast, Naval Civil Engineering Lab, were going to put a rack down at 5,300 feet, where they would have an idea how this thing would react to stress corrosion. You're down there under pressure and you have little currents moving around. So we put our sphere, our 1/5 scale sphere there. We put part of our, next one, our buoyant material. And this is what the rack looked like that they were going to lower out there in the Pacific, not too far from Point Mugu, down to 5,300 feet. Now their plan was to lower it. If you can envision this, they lower the rack, and it has a guy, a wire up to a point, to a float. The float, though, was 200 feet below the surface. And it had another loop down here where it could release this part at a certain sonar signal, a certain frequency. And they were going to retrieve it in 6 months. So at the end of 6 months, they went over that area and tried to get that thing to come back to the surface. Couldn't do it. 3 years later, it worked. And they brought this rack up, and now we had something that would show us, we had buoyancy material. We call this, we made various mixes. In other words, so much of the glass beads, microspheres, so much epoxy resin, and so much catalyst. We were trying to get a proper mix, about 40 to 42 pounds. And we found the best combination was about 40.1 pounds. And we could mix this in the the explosive mixers up in China Lake, salt wells. You could mix it in that, and you could pour it into any form you want. And then it would harden, and you could machine it like it was a piece of wood. Very easy to work with. So we put a piece in there. The only problem is after 3 years underwater, you know, you have about a 1 to 2 current movement down there in the rack. This thing is afloat. So it's trying to get loose, trying to get loose, At the end of the 3 years, we never found it. It broke loose. So somewhere in the Pacific, this thing is floating around. Next one. It was lowered again, and we were able to get a good idea of which one was the best aluminum alloy to use. And we found out A356 could take more pressure in our test chambers than the 220. Next one. This is what it looked like after 3 years. Our electrical connectors still function. All we had was a little deposition on the sides, which you brushed off. Nothing wrong with it. Now the hatch design, well, there's quite a ways to do this. We took it from submarines, very simple. You undog the hatch, open it up, next. And that you had springs here so that once you opened it, it allows you to open it easily. You just push it open. You could pull it down, and then once you pulled it down, you could just rotate that, and you drive out the locking mechanism to go in alongside here, and that was it. And after you had it in water, the pressure on top of that thing, you couldn't open it. We had seals around here, O-ring seals, so it was watertight. Elle has experience opening that thing several times. Now, there was a thing we had to do also. The environmental system. You had a sphere here now you had to provide a life support from. They're in this thing, they're breathing oxygen, the air, and exhaling carbon dioxide and moisture. Okay, so how do we design this thing? What kind of life support system do we come up with? So a few of us went and checked the Mercury program, the spacecraft, and they were using good instrumentation, but they were filling their operating sphere, if you will, their operating area, with pure oxygen. And one of the things we tried to do in the lab, we tried to have a sphere represent our control sphere and get in it with a simulated instrumentation panel, and we simulated a hot wire, a fire potential. And we found out we could not put it out in a true oxygen environment. We couldn't put it out. So the concept, we had 2 flight surgeons with us, Lieutenant Steve Tope and Lieutenant Tolman, and they would examine us. We'd go in there and do things, and they watch our body reactions. And they said, we all agree, we cannot be in an oxygen environment. So we decided to have everything in that sphere, just like you hear here. Normal conditions, 14.7 psi, 16% oxygen. So that as you're in that sphere, and you're taking the oxygen and reducing it to carbon dioxide and moisture, we have scrubbers that remove that. So you're progressively lowering the pressure in the sphere. And when the sensor sees the pressure go down to about 14 psi, it bleeds in outside oxygen until you're back up to 15 psi. So that's what we had in the sphere. And about 3 or 4 months after we decided to do that, that's when they had the accident in the space program where those 3 astronauts were burned because they couldn't put out a fire in that capsule. Next. Oh, what I'm showing, let's go back to that one. In order to have an emergency exit procedure, something goes wrong in the sub, how do you get out? Well, we had a way in which they would put on what we call a Steinke hood. Now the Steinke hood has an oxygen supply of its own. So they could bleed in outside water while they're in there with this, and as they're bleeding water in, they're breathing oxygen that's compensating, adjusting to the pressure that's coming into the sphere. Eventually you're at the same pressure as the outside water. So now you can undog the hatch and get out, and you make a free ascent. You don't try to swim up, you follow your bubble zone. And as you're coming up and inhaling oxygen, the oxygen is getting used to the pressure around you. So your body's compensating for the pressure of the sea around you as you make your ascent. And this man, Commander Lincoln Lippincott, we call him Link, demonstrated how you could get out of a submarine at 450 foot depth. He went into the, I don't know if you're familiar with the forward torpedo room in the submarines, but you go into this little area and you close the door behind you, the hatch, then you open, you pressurize that to be the same as seawater above you. Then you can undog this. So he exited the forward torpedo room and got on the forward part of the submarine with this stanky hood, and he made a free ascent from 450 feet. He demonstrated that you could make an egress from a submarine as far down as 450 feet. So this is the system that was adapted for our operators when they operated Moray in case we got into a situation where they had to get out of the submarine. Next. This was the Astor torpedo motor that Westinghouse designed, and one of the things we had to do, get the next one, when we proposed to use this, we had the propellers going in this direction, which gives us forward thrust. We had someone in upper command, not mentioning any names, said that, do you have the capability of reversing this engine, this motor? And at the time he was addressing this, I was standing right alongside Commander Link Lippincott and Dr. McLean. And this, can you reverse this boat? Have the motor go in reverse? And Commander Lincoln, seasoned submariner, said, sir, he said, we don't back submarines down. We can go in reverse when we're down there, but we don't back them down. So this person said, well, you will have that feature, that reversing capability in this boat, or you don't go to San Clemente Island and test. Okay, so what do? You contact Westinghouse and say, we need a reversing capability in this torpedo motor. Oh, we can do it. It'll take 6 months and $400,000 and so on. I said, wait a second. It's a DC motor. Let's pull the end bells off, make a duplicate set of slip rings, put one on the front, put one on the back. That was the Don Jackson, a few other of us. Said, this is a DC motor. So we went to our engineering department, the shop. They made these slip rings for us. We put them on that motor, and Dr. McLean invited this person to come to the front one wing in the lab and say, sir, would you like to see the motor in operation? And we had the disc to show the spinning torque. He said, this is forward motion. And we have a little simple switching operation. This is reverse. Can we go to San Clemente? And he could not say no. So we went to San Clemente testing. Next one. This is the back or aft control fin section, which houses the motor. And this is where we had to mount the fins. This is the part that's simply bolted on to that big ring that held the upper and lower half of the hulls. Next. And this is the little package itself that fit in, the 3-blade and the 4-blade. You have the 3-blade? You still have it? I have the 4-blade. It's now 2 blades and mine is now 3 blades. There was a little accident, but not on our watch, right? Okay, next one. When you have this fin in place, and there's 4 places for them, by the movement of the control stick column, you could get the boat to go down, go up, or make turns to the right, or make turns to the left. And the fins would follow the movements of your hydraulic control. The major portion was laminated fiberglass, epoxy resin, the buoyancy material, and these parts were stainless steel that was supporting that. So most of that fin, next one, is fiberglass, plastic, and buoyancy material. And here's the way it was captured, and this is the way it interfaced with the controls section. Next. This gives you an idea how Al and the other operators would use that Cessna type control and be able to move these fins either together or separate, so they'd have ability to move it up, down, right and left, etc. Next. That's what it looked like. And there's the actual unit that was put into the sphere. Next. This just shows you the hydraulic act. The system was hydraulic, manual hydraulic, so you'd push it forward and the pressure would move those fins. Next. The basic system was an idea what we wanted to do, but Vern Carlson, who's no longer at the group, he's not even in that picture, he left us a long time ago, but he was very, very knowledgeable with these kind of operating systems. So we had people with talent in various, so we had an electronic group, we had a aerodynamic, hydrodynamic group, and that's what you need when it's a team effort. This is no one man's idea. Even though Dr. McLean came up with it, it took all these people to make it a reality. Each had special talents, each one contributed, very much involved in every aspect of building and testing. Next one. This is the way you had a pass-through, because you had to do something in the control sphere, electrically communicate with the electronic sphere, and that did other things too. So we had what we call high pressure connections that would go to those reinforced areas in the control sphere. Next. This is what they look like. And we checked them out at least up to 3,500 psi. So we knew it was safe to use these in our application. Next. And this is how we had the control sphere talk to the electronic sphere. Next. We also had to have hydraulic bulkhead connectors that could go into these areas of our aluminum sphere and take that pressure too. So these were checked out to 3,500 psi. And this gives you a little idea. Now you have to have trim. You can trim out an aircraft. How do you trim out a submarine? Boy, if you trim it out, you have two reservoirs. And they were partially filled with mercury. So that by applying air pressure on this part, you could transfer some of the mercury forward, or applying pressure here, you could apply and drive some of that mercury back, so the operators could trim out the craft by simply moving around and moving that mercury. Next. This is how they were mounted. This is in the forward part of the sphere. And here you'll notice how that little hat section was made so that when we slipped the upper half on top of that, we would come through with bolts and lock in to connect to these embedded nuts. So we simply slip the upper half down and then run our guns and attach it. Next. The life support system. I was mentioning how we had oxygen come in, but we also had another feature. If something happened in here, we could fall back on what we call a rebreather. They could simply put on something that was a complete operating system of its own. They could have something to supply them with oxygen while they try to fix whatever problem is in the control sphere. If it was too severe, then they'd make the egress with the Steinke hood. Next. And these are the scrubbers I was mentioning. You had a CO2 absorber. Typically, you'd have lithium hydroxide in there. You had scrubbers where you had charcoal absorb the moisture. Then you had the cabin pressure regulator. This is one of the things we borrowed from the Mercury program. It was very instrumental in regulating the atmosphere inside our control sphere. Next. This is the independent rebreather system, that if they had a problem in the capsule for some reason, they could individually put these out, and they had its own oxygen supply. We're getting further along now. We have the control section fairly well along. We have the battery pack, pressure vessel. We have the control sphere and the electronic sphere. We're getting ready to assemble this thing. Next. And there's a little different view looking at the same thing. Now, one of the things we had to do is make sure that when it came time to recharge the batteries, you could take the battery pack after you remove the upper hull. Take it out, and then pull that pack out and do the charging and recharging. Next. This is our communication system. We had an SQS-19 sonar system, and we had what we call our communication transducer, where we could have an underwater telephone, if you will. And this is how it was mounted. Here's that front ring. that high alloy steel ring to which the hull was attached and the nose cap was attached here. And we had frames in it so we could mount our sonar system and a few other things up in front. We had a TV camera that we could move up out of the hull and look forward. We also had one below. We had the monitor in the control sphere and what we call the electronic package that would operate that. And this is how that TV camera, or TV unit, was mounted. Now, the front is over here. You're looking at from the electronic sphere here, just ahead of it. And that's how it was mounted to one of these supports of that big ring. And there you're looking at now. This is the electronic sphere, and there's the TV camera. And what you see here is a protection, because we machined that ring where they're bolted together, be very precise. It had to have a double groove for a double O-ring, so that we could bolt that together when we put this together. Once you had it bolted together at low pressure when you're going down, it's sealed. After you were down a depth, the pressure, you couldn't open that if you tried. Next. This is L's concept of what we should have in the control sphere in the way of instrumentation. Aircraft type communication. Next. And this is what it looked like. How did you feel when you were up in that front seat?
Fine. It was a lot of fun.
Is it much like flying your plane?
It was totally different than flying an airplane. Airplanes how it had the instability capability there, and this was very stable. The center of gravity was low, and so it essentially always stayed bottom down, pointing down, unless you made a real tight turn at high speeds. And because of the center of gravity being
shifting,
low, you'd actually bank it a bit, but you weren't doing that banking with any of the controls.
The Moray vehicle was a very, very stable boat. And a lot of things that we did with that, we have what we call a quickening system. If you're in here and you have a target and you want to approach that target, well, are you going to be watching this instrument, this instrument, this instrument, this instrument? You can't do that. So everything was presented in a quickening fashion to one screen. It had the target bip here, and you are here, and it gave you the curve to follow, and you just steered the curve, which was adapted to a certain extent in later submarines. There's a lot of ideas that came out of Moray, even though I'll tell you about that a little later, it never got to be a tactical weapon, which it should have been.
I might be able to give a little more information on that quicken beater. Initially, the way we would fly the boat was if you wanted a particular depth, you would essentially dive until you got close to that depth, and you dive just by pushing the stick forward, and you had an indicator as to tell you what angle that you were diving at. And then you would, when you got close to the depth that you wanted, you'd back off and you'd try to level off. Well, the controls, the hydraulic controls, which were just manual, there was no mechanical help there to it, and the receivers and transmitters in the hydraulic system were not perfect, so they had hysteresis. So if you kind of gave it a forward stick and held it there for a while, and then wanted to get rid of a little bit, you'd have to get rid of part of it, which would do nothing, and then you'd give it a little more, and finally the controls would move and it would take effect. Well, what the quicken meter did was combined the instrumentation, or instrumentation showed you what the fin deflections were, and of course what the altitude, what the depth was, and you would just try to match those up to maintain depth. But with a quicken meter, we electronically dialed in a signal for the depth that we wanted. And then we brought the position signals from each of the fins into a summing circuit. And when we got done with that, we had a little cross meter there that all you had to do was just keep the needle centered, and you would dive to the depth that you wanted, and you would roll out just by maintaining that center meter reading right down to 0, and it made all the difference in the world. And we weren't really able to run it at full speed until we had that capability built in. And apparently that system was, there was a publication made on it, and apparently that was the same scheme was used in the control system of several of the active torpedoes.
Right, yes. Next. That's just the back side of the control panel. Next. This is the final product. Not very much room in there. Unfortunately, we didn't have people who were 6'9", about 400 pounds. We did have one operator, Wayne Rouse, who was over here, who was 5'6", weighed 145 pounds, and as strong as could be. And when he was relieved of duty, his replacement was an officer that came into the branch, and he said, "I'm your replacement." And I said, "You are who?" And he said, "My name is Stretch Leonard." 6'5". And I'm thinking, I don't know if he ever could squeeze into the people back in Washington. You said you wanted someone in this range. Stretch Leonard appears. Next.
This Wayne Rouse was Dick says he was a very strong fellow, and he was. And several places in the cockpit and so on, there's valves that we had to secure and so on. And when he secured it, I mean, he secured it.
You couldn't take, you needed a wrench to get it off.
Couldn't get it off of the stop. And,
Okay. We're getting there, getting to the point where we almost can start final assembly. You can see that we even painted the thing so that we could observe it underwater easier. Everything is mounted in the front. The control spheres, of course, they don't have their upper halves on. Battery pack and the back end is in place. Next. Buoyancy material. Remember I was saying we needed positive buoyancy. How do you get that? Well, we could mix the material out of salt wells and mixers, take this thing, turn it upside down. And where we had the ribs, we would put spacers in and just pour that into that area, and we had a mold. When we got through, then we kind of machined out places where it would fit over the battery pack. And these things were locked in place into the upper hull. So this was put into the major interstices that were in the hull. Another view. This is the material that we came up with. And we put this out. I wrote a publication on this, and we thought it was China Lake's patent. Well, one of our former branch heads, I won't name him, went to work for General Motors. And I happened to be in Washington, D.C. in 1960 when they had the World's Fair. And I had to stay over the weekend, make more presentations. I said, I can't be in Washington when they have a World's Fair going on in New York. So I went to New York to go to the World's Fair. And as I'm walking around seeing all their exhibits, I saw General Motors exhibit. And here they had this big thing out there. They invented syntactic foam. They had blocks of them. And when I came back, Leroy Riggs was our acting TD. I said, how can they do this? We published data on this. It's a Navy idea. And we got a hold of JAG people and said, can we sue General Motors? And they said if they change our amount of glass beads, the epoxy resin, and catalyst by 1%, then you have no right to that patent. So JAG told us we could not go after General Motors, and they got all the credit for coming up with buoyancy material. Next. This is how you see it actually in the upper hull. Next one. And this is how we put it around the openings, packed it in, slipped it in. The openings are in the control fin area. Now you would think, if you had high-ranking naval officers come to the base, this is the Vice CNO, Ricketts, Vice Admiral C.B. Ricketts, second guy in charge. This is the head of operations in the Navy, Griffin. They came, they were enthused, he even got in. That's almost like Stretch Leonard getting in there. And they liked what they saw. We're thinking if these people that represent the highest rank in the Navy approved of what we were doing, this is a goal. We will have something that we demonstrated a prototype, and we were able to get down and do the Moray 2, which was the tactical fighter. We were ecstatic. That's Frank Niemeyer, our department head, and I couldn't be happier that day. Anyway, they came. We said, my God, this is it. We have approval. Next one. Now this is an idea what we had in the way of a safety feature that they didn't have on Surf Coupe. We could pop a float. We were in trouble, we were down, and this one go all the way to the surface, and it paid out a wire. And we could send down a heavier wire, cable, which had an engagement, a clamp. There was a feature here where we could lock onto a hard point, like an eye. We could lift the entire boat up by that mechanism, because it was almost positively buoyant. Next we had bottom sounders. Here's where we had our TV. We had things that made this thing very safe. Next. This is the device that was put into that little pocket between the control sphere and the electronic sphere. And we demonstrated this first. We were allowed to get this boat wet. I go to the next one. This is what it looked like. Next one. This is snort track water basin. We were able to bring the Moray out to the snort track water basin and have it submerged for the first time. Next one. We also made sure we could do this at San Clemente Island as though we were in the boat, and we popped that float down deep. It came to the surface, and we could run another wire down, another cable down to get it. So we demonstrated it here at China Lake, and we demonstrated it at the San Clemente Island. Next one. We had to build a transport fixture to move this around here on the base, also to move it around there at San Clemente. So this was done at China Lake. Next one. And this is how we moved it around from where we had it in Michelson Lab in the back end there. We're moving it down towards the water basin there at the end of snort track. We had what we call drag discs. We could, when we get into the snort basin, next one, you can see those are, when you lower that, lower it, that's Bob Montrose getting in there. Next one. Now we could operate the propulsion system, but we won't have any thrust. The discs are spinning, but there's no thrust. So we could see if the motor's working the way it should be. We could check out, very easily check out a lot of the systems in this 14 feet of water that we have at the snort track water basin that used to slow down the sleds. Next one. And then you could take the upper half off and do some testing where you can observe what's going on. Next. How do you handle Moray at sea? So we developed a catamaran. It was, concept was here, and it was built here, Salt Wells. Next one. And here we have it. It's the mothership for Moray. In other words, when we get out in open water, we could take and harness Moray to it and bring it to the area, the test site, and guys like L or the other submarines would get in, close the hatch, then we'd lower it into the sea, because it only had about that much freeboard. But it was able to give us something that we could maneuver Moray around while we're at San Clemente Island. Next. Now, we were a little careful. This is only, we only have one Moray. And we wanted the riggers to know that they were handling something that we didn't want them to damage. So we build a barrel cluster, kind of the same diameter, same length, and they're partially filled, so they give you a sense of handling moray, size, weight, diameter, etc. Train our riggers on how to handle this thing before we get down to San Clemente Island. A story about that. We had someone from the Secretary of Defense office. He was number 2 man. Robert McNamara, number 1 man. So Dr. Brown came here to visit China Lake. And we had moray on display for him. We had the models and everything, and tell this man what we're doing. And we're in this first wing here, and as you go out the wing, we had ground round, which is now called chaparral. And we had the big flare that went into pound can power flare. We had all these things for him to see. So here we are with tables with some of the things that represent what's in moray, miniatures of them. And he's here, Dr. McLean is here, and we're behind him, and he's more or less pushing Dr. McLean along, not even giving him a chance to explain what we had in the boat. And then when he went around the outside, we had the barrels. We call it the barrel cuda. Now, our commanding officer was Captain Blenman. Captain Blenman was with Dr. Brown. So they're out there and they're looking at the big flare, they're looking at chaparral, and Captain Blenman comes running back. And he said, Dr. Brown wants to know what's the significance of these barrels. I'm thinking that's the only question he asked. So Charlie Jenkins was branch head at the time. So Charlie looked at Captain Blenman and said, tell Dr. Brown that anything that size is obvious. And then Jenkins walked away. And we're looking at Blenman and saying, is he going to tell that to Dr. Brown? That's how the barrel cuda became famous. Now, how do you get the boat down to San Clemente Island? We flew it in a C-124. Came here to Armitage Field, next one. Put it in. You lose it inside that airplane. We flew this to San Clemente Island, next one, and unloaded it there. Now, when we went to see Jacques Cousteau, I remember telling you that story at San Diego. The Navy hired him to bring his little diving saucer to check the La Jolla Trench and the San Diego Trench. And he was telling us they did a first, Jacques Cousteau. He said, we're the first ones to ever fly a submarine in an airplane, that little diving saucer. And Commander Linklip and I said, we can't burst this bubble and tell them that we flew moray down to San Clemente Island long before he ever flew that little Surcouf to San Diego. Next one. Now, when we get up to San Clemente Island, we're moving it towards the Wilson Cove area, which was our test area. Next one. We're training the riggers from the barge on how to handle our moray. This is the exact system that we would raise and lower moray out of the water. Next. Now, for the first series of tests, we locked the fins in place and we took the propellers off and blocked that because we want to do other kinds of tests, drop it down to a certain depth, about 1,000 feet, and see if there's any leaks and things like that. So, next one. This is the way it looked going out. This is the pier at Wilson Cove, San Clemente Island, and there's the barge we're going to be operating from. Next one. Again, this gives you an idea how the moray would be taken off its rack as land transport, dropped in the water, and the divers would unhook the crane mechanism. Next. This gives you an idea what we were living with. You know, don't make any mistakes, don't drop it, don't do anything wrong. Go ahead, next. This is getting ready for its first exposure to seawater. Next. Now we have people here. When you work at San Clemente Island, it came under the direction of the Underwater Department in San Diego. In Pasadena. That was another branch of NOTS at the time. So the Underwater Department had control of San Clemente Island. So when you went there, you operated with their people. So you have some of the Pasadena people, and there's Bob Montross, there's myself, and Wayne Rouse, and we had two famous visitors. This man dove down and was one of the few Navy men that went down in the Trieste. And they wanted to see what we were able to do with our little submarine. Trieste is nothing more or less than a big elevator. What they do with that thing, that big thing you see on top, is a float. And they've flooded down, and it now has negative buoyancy, and it sinks. And it goes all the way down, like an elevator. And they went down to the bottom of that Mindanao Trench, 37,000 feet. Brought it in, and no capability down there. It just moved around about, what, 1, 2 knots, wiggling around with water pulsars. And they'd drop metal shot, steel shot, regain buoyancy, and come back to the surface. When we went aboard that thing, it was something else. We learned that there's a lot of do's and don'ts in building submersibles. Anyway, next one. When you have this boat in water, we wanted to see what the currents were doing to it, how it was reacting. I mean, we had a little buoyancy, so we were watching the changes in its weight, that meter. And the only two taking direction were Montrose and myself. The others they're there for the ride. And we're thinking, we know we have to be in your backyard, but can't you get involved? Next one. Divers would come down, unhook the mechanism, and now we were able to do things with that boat. Next one. We had to have that catamaran brought to San Clemente Island. So we brought it to Long Beach Naval Facility. Then from there, next one, put it in the water. And this is a Navy crew that's operating the catamaran and bringing it to San Clemente Island. Next one. And this is the way we married or moored Moray to the catamaran to bring it out to the area where we're going to test it, in the Wilson Cove area. And then next one, we had the catamaran on station, so that when it came time for them to surface, we would go over there, hook onto it, and raise it up and bring it back. Next. First, were you on this one? The first one? This is the first time we were operating the boat. Actually, the first thing we did with the boat was make it go down in reverse. We took, videos. We made sure that this military person understood we had a backing down capability. So once we did that, we said, okay, now let's get on with what we're supposed to do. And this is one of the first runs that was made. Next. Again, submerging. And Al and who was with you? Montrose. They did a power ascent. Well, from 400 feet? 400? I thought it was 400. This is what happens when you have a little buoyancy and the capability of this boat powered. It came out almost half. In fact, the water in the boat surged forward, and we found out that we had to reinforce the way we locked that nose shape to that forward mounting ring. That was a ride for you. Next.
It's kind of a funny story behind that. They had some Navy high, officers that were out visiting, and they watched some of the runs that were made and so on, and they asked, could we make it broach a bit, and I was a pilot at the time, and so I asked him, how much do you want? And he said, well, just enough to make it interesting. And so running about 50 feet, not very deep, and not running real fast, and kind of pulled it up, and the boat kind of came out a bit, nothing like that picture. And they said, well, that was good, but can you make it substantially more interesting? And I said, okay. So
you made it more interesting.
We got a running start at it, much faster, and starting out much deeper, and just pulled it up, and it kept the power right there until we broke the surface. And then it would kaploosh down, and it actually ruptured that nose cone, and it was about ready to fall off because it was built for going forward, not sideways. And so that was the last time we did that.
What I'm trying to show you is the team and they're up there, and I'm going to give the names of every one of them. that took part in this, the submariners, the civilians involved. And we started this program in October 1959, and we finished our phase of it in 1965. And then the base, for some unknown reason, reorganized, and they put our particular underwater branch into another division. And from then on, most of the employees that were in the program were asked to go somewhere else, or if you wanted to. And most of it said, under the new command, yes, we'll go somewhere else. The program was brought down to San Diego, NOSC. And from NOSC, they moved the operation to Oahu, Kaneohe. After all this time, you have the boat demonstrate this capability. Then we had to go to view ships to have them review the program and get authority to go to San Clemente Island. We had 2 senior captains from view ships come down, great guys, wonderful people. We gave them a 3-day presentation. They went over every aspect of the boat, the design, and they approved it. Based on their approval, then we were able to go to San Clemente Island. They looked at all our safety features, etc. Now we had a boat that did everything that Dr. McLean was projecting. And you go to the CNO and you say, well, now can we build a prototype? And you're facing an admiral who tells you point blank, he's not going to split the Navy one more time. That was Admiral Red Ramage. And you can't understand what he's saying. And you say, sir, split the Navy one more time? I don't understand what you're saying. He said, well, listen. He says, up until 1900, we had surface ships. 1 command, 1 school pattern, 1 career. After 1900, we had the submarine come in. We split the Navy, 2 commands, 2 career patterns, 2 schools. After World War I, we had the carrier come in. That's 3 commands, 3 career patterns, 3 schools. After World War II, we had nuclear conventional. We had 6 navies, surface ships, submarines, aircraft carriers. He says, you're coming in with a small boat, and that's going to split the Navy one more time. I'm not going to allow it. And that was the end of Moray being a tactical underwater fighter. It became a research vehicle. And I personally feel this bothered Dr. McLean so much that he left China Lake in 1967, and he went with NOSC. They eventually formed that new Naval Oceanographic group down there. He had a love of the ocean. In fact, he was one of the few people that recognized the importance of studying the dolphin for Navy applications. He was so far ahead of his time that I think it bothered him. He was so close to having a reality of an underwater fighter, because with that thing, you could locate, identify, and remove a threat whenever it posed a threat to your warship group or your submarines. Now, you say, where does this go? That was 40 years ago, right? 40 years ago. The latest submarine built and put into service, the USS Ohio, the newest billion-dollar submarine. It has something on its deck. And in that something on its deck is a small submersible. What do you think Moray could have done? It could have been on the deck there. They're using this, they say, for covert operations. You can bring special forces ashore and SEALs. But anyway, this is where Moray could have gone. 1965. That's it. Any questions? Yes?
What happened? Where is it? Where is it now?
That's a big question. We have been trying for almost 8 years now to locate Moray. The last we heard, when they went to Kaneohe, was research vehicle, just using for oceanographic studies, that it was in a building at Kaneohe Bay. We've been trying to track it. We have had people going to Hawaii and Oahu there because they said it could be in one of the sea parks that they have just up there as a display. We have never had any success in finding out what happened to Moray. And I don't understand this because
I've been told that it's on display at a private museum. I'll have to find out who told me that and make sure that they weren't blowing smoke.
It's in
but-
private hands.
Yeah, that it was in private hands, but that it was on display. Now, I can't vouch that that's true or
would you
not.
follow that up?
I will. I
Good,
will.
okay. And let our people there in the museum know, because what we want to do is bring that back to China Lake and have it a part of our museum.
Sure.
Any other questions? Well, thank you. I hope I haven't bored you.
Well, thank you very much, Dick. I have a certificate for you as well as your own copy of the poster. And I would also encourage any of you, if you're going to make a trip to the museum anytime soon, you might want to call ahead and see when Dick's giving tours, because he's certainly a wealth of information. A special thank you to the museum for our display today. I believe this is the first showing of the photos, and we get to keep them through midweek next week, so please take some time to look at those. Thank you all for coming.